What if everything you thought you knew about gravity was only half the story? Picture this: the force that keeps your feet planted on the ground, the same one that holds planets in orbit and shapes the cosmos itself, might not play by the rules we think it does. At the smallest scales of the universe, where particles flicker in and out of existence and space-time itself twists like taffy, gravity as we understand it just falls apart. Welcome to the greatest unsolved puzzle in physics, quantum gravity. For over a century, scientists have been piecing together the fabric of reality, from the bizarre rules of quantum mechanics to the cosmic dance of general relativity. But when these two titans of physics collide, the result isn't harmony, it's chaos. A black hole shouldn't be able to erase information. Empty space shouldn't fizz with energy. And yet, the universe doesn't care what should be, it does what it pleases. This isn't just some abstract academic debate. Quantum gravity is the missing key to unlocking the deepest secrets of existence. What happened at the very first moment of the Big Bang? What truly lurks at the heart of a black hole? Is there a way to reconcile the infinitely large with the infinitely small? These aren't just questions for physicists in lab coats, they're mysteries that tug at the very nature of reality itself, and the wildest part, the answers might already be hiding in plain sight, scattered across decades of radical theories, each one more mind-bending than the last. From vibrating strings to loops of space-time, from holographic universes to hidden dimensions, the candidates for a theory of quantum gravity read like something out of a sci-fi epic. But here's the twist: any one of them could be right, so buckle up, we're about to take a journey to the edge of human understanding, where the rules of physics blur and the universe gets weird. We'll dive into 30 of the most startling, provocative, and downright brilliant theories that attempt to crack the quantum gravity code. Some will sound like pure fantasy. Others might just hold the seeds of a revolution, but one thing's for sure: by the time we're done, you'll never look at gravity the same way again, ready to have your mind stretched. Let's begin. Let's start with one of the most radical reimaginations of space and time ever proposed: loop quantum gravity. Forget the smooth, continuous fabric of the universe you've seen in diagrams. This theory suggests spacetime isn't a blank canvas at all. Instead, it's stitched together from tiny, indivisible loops, like a cosmic tapestry woven from threads a billion times smaller than an atom. These loops aren't floating in space, they are space, twisting and connecting to form the very geometry of reality. The idea was born from a simple but profound question: if everything in the universe, light, matter, energy, comes in discrete packets, why should spacetime get a free pass? In the 1980s, physicists like Carlo Rovelli and Lee Smolin took this puzzle head-on, applying the rules of quantum mechanics to Einstein's general relativity. The result: a universe where not just particles, but the stage they perform on, is quantized. Picture a pixelated video game where the resolution is so fine, you'd never notice the blocks except at the tiniest scales, where the graininess of spacetime becomes impossible to ignore. Here's where it gets wild. In loop quantum gravity, there's no such thing as infinite smallness. You can't keep dividing space into ever tinier pieces. Eventually, you hit a fundamental limit, like the smallest possible stitch in that cosmic tapestry. This solves some of the most glaring paradoxes of black holes and the Big Bang, where classical physics breaks down into nonsense. No more singularities of infinite density, just a universe that rebounds or transforms when squeezed too tightly. But the theory isn't without its critics. For one, it's notoriously difficult to test. These loops exist at the Planck scale, a realm so small that probing it would require particle accelerators the size of galaxies. And while it elegantly quantizes gravity, it doesn't yet explain why the other fundamental forces exist. Still, that hasn't stopped physicists from chasing its implications, like the possibility that black holes could tunnel into white holes, or that the Big Bang was actually a big bounce from a previous universe's collapse. Loop quantum gravity forces us to confront something startling. the universe might not be a smooth, continuous entity, but a shimmering network of relationships where space and time emerge from something deeper. It's a reminder that even the most fundamental truths we take for granted, like the emptiness of a vacuum, might just be illusions at the right scale. If loop quantum gravity is correct, the very foundations of reality would rewrite some of cosmology's most dramatic moments. Take black holes, those cosmic monsters where gravity crushes matter into oblivion. In Einstein's universe, their hearts are singularities, points of infinite density where spacetime curves into a bottomless pit and physics itself surrenders. But loop quantum gravity tears up that script. Here, spacetime's pixelated nature means gravity can't squeeze matter beyond a certain limit. Instead of a singularity, you'd hit a ceiling, a point where the loops of spacetime push back, turning collapse into a rebound. Some theories suggest a black hole's core might spit matter back out as a white hole, like a cosmic trampoline hurling everything it swallowed into a new region of spacetime. Then there's the Big Bang. The classical story paints it as a fiery explosion from nothingness, a singularity birthing the cosmos. But loop quantum gravity offers a twist. What if it wasn't a beginning, but a turnaround? Imagine a previous universe collapsing under its own weight, only for quantum loops to reverse the collapse into our Big Bang. No mysterious creation, just an eternal cycle of contraction and expansion. This big bounce scenario erases the need for a singularity altogether, trading cosmic birth pangs for an endless cosmic heartbeat. But how do we test such mind-bending ideas? Enter the painstaking work of observational cosmology. Some researchers hunt for echoes of a pre-Big Bang universe in the cosmic microwave background, faint patterns in leftover radiation that could hint at a bounce. Others study evaporating black holes for anomalies in their death throes, searching for quantum gravity's fingerprints in their final bursts of energy. There's even the tantalizing possibility that spacetime's granularity could subtly alter how high-energy particles travel across the universe, leaving traces in gamma-ray bursts or neutrino detectors. Yet the biggest hurdle remains scale. Probing spacetime's loops directly would require energies 1 trillion times beyond our most powerful particle colliders. So physicists get creative. Tabletop experiments with supercooled atoms or precise measurements of gravitational waves might reveal indirect clues. Some teams even simulate loop quantum gravity's effects using ultra-thin materials in labs, where electrons behave as if they're moving through warped, quantum spacetime. The beauty of loop quantum gravity lies in its audacity. It doesn't just tweak our understanding, it demands we rethink the stage itself. If space and time are woven from quantum threads, then reality isn't a fixed backdrop but a dynamic, evolving network. And that raises an even wilder question: what if the stitches of this cosmic fabric change over time? Could the very speed of light or the strength of gravity shift as the universe's quantum architecture evolves? For now, those remain mysteries waiting in the loom. Now let's unravel a theory that turns the very idea of particles inside out literally. String theory doesn't just tweak our understanding of gravity, it rewrites the entire cosmic rulebook. Forget dots of matter or even loops of spacetime. This framework suggests that at the most fundamental level, everything in the universe is made of tiny, vibrating strings. These aren't the strings you'd find on a guitar, but unimaginably small filaments of energy, each one dancing to its own unique frequency. Pluck one string gently, and it might vibrate as an electron. Strum it with more energy, and suddenly it's a quark. The entire symphony of particles we know, the building blocks of reality, could just be different notes played on these cosmic strings. But here's the catch: for this elegant musical metaphor to work, the universe needs more than the 4 dimensions we experience. String theory demands a staggering 10 dimensions, maybe even 11, all curled up so tightly that we'd never notice them. Picture an ant crawling along a phone cable. From afar, the cable looks like a simple line, but up close, the ant sees it's a cylinder with hidden dimensions of width and curvature. That's how string theory imagines our reality, with extra dimensions coiled into shapes called Calabi-Yau manifolds, each one influencing how strings vibrate and, in turn, what particles emerge. This isn't just mathematical whimsy. Physicists like Edward Witten, a titan in the field, saw string theory as the missing bridge between gravity and quantum mechanics. In Einstein's world, gravity is the curvature of spacetime. In string theory, it's the lowest energy vibration of a closed string, a graviton, that flits between other strings, weaving the fabric of attraction we feel. Suddenly, gravity isn't an outsider, it's just another note in the quantum symphony. Yet for all its beauty, string theory has sparked fierce debate. Critics point out its lack of testable predictions after decades. We still haven't found those extra dimensions or detected a graviton. Others argue its many possible solutions, each describing a different universe with different physics, make it more of a meta-theory than a single, concrete framework. But supporters counter that this very flexibility might be its strength. Could the multiverse, a vast collection of universes with unique laws, be a feature, not a flaw? String theory also gives us startling possibilities, like brainworld scenarios where our entire universe is a three-dimensional membrane floating in higher dimensional space. Collisions between these brains could explain cosmic mysteries like the Big Bang itself, and if strings are real, black holes might not be infinitely dense points but tangled knots of stringy energy, rewriting their terrifying paradoxes. Love it or loathe it, string theory challenges us to think bigger literally. It stretches the imagination across hidden dimensions and whispers that the universe might be far stranger, far richer than we ever dared suppose. Whether it's the final theory or just a stepping stone, one thing's certain: in the quest for quantum gravity, it's a melody too compelling to ignore. String theory's boldest claim isn't just about hidden dimensions or vibrating filaments. It's the unsettling idea that our universe might be one of countless others, each with its own unique laws of physics. Picture a cosmic library where every book tells a different story of reality, with alternate versions of gravity, particles, even time itself. This landscape of possible universes emerges from string theory's math, where the way extra dimensions curl and twist could produce nearly infinite variations. Some might have stars that burn out in seconds, others could be so devoid of structure that matter never clumps into galaxies, and somewhere in this vast ensemble, there's a universe like ours, where conditions just happen to allow atoms, planets, and life to emerge. This multiverse scenario divides physicists like few other ideas. To supporters, it's a natural consequence of string theory's equations, a feature, not a bug. If the universe's fundamental constants seem finely tuned for life, maybe it's because we're in one of the rare pockets where they align just right. No divine hand needed, just statistics on a cosmic scale, but critics fire back with a devastating question: if a theory predicts every possible outcome, does it actually predict anything at all? Without a way to observe these other universes, string theory risks becoming untestable, a beautiful mathematical construct trapped in the realm of philosophy. Even its cultural footprint is polarizing. String theory has inspired everything from blockbuster films to midnight dorm room debates, often oversimplified as the theory of everything. Yet that hype can backfire. When decades of research haven't produced a smoking gun experiment, public disillusionment grows. Some argue this pop science prominence has actually hurt physics, diverting talent and funding from less glamorous but more testable ideas. Others counter that string theory's very ambition pushes mathematics to breakthroughs that ripple across science, from black hole physics to quantum computing. Here's where things get meta. If the multiverse is real, could we ever find proof? Some theorists hunt for cosmic bruises, anomalies in the microwave background where our universe might have collided with another. Others simulate brain collisions in supercomputers, tracing how such crashes could imprint on the fabric of space. And then there's the wild card: what if a higher dimensional civilization left clues in the constants of physics, like a signature etched into the very laws of nature? Whether you see the multiverse as a thrilling frontier or a dead-end metaphor, one thing's clear: string theory forces us to grapple with the humbling possibility that everything we know might be a tiny footnote in a much, much larger story. And that raises a haunting thought: if there are infinite universes, are there infinite versions of us, each asking the same questions, or is our curiosity itself the rarest cosmic accident of all? Imagine building the universe from scratch with nothing but microscopic triangles. That's the bold gamble of causal dynamical triangulations, a theory that strips spacetime down to its geometric bones. Unlike string theory's vibrating filaments or loop quantum gravity's woven threads, this approach treats reality like an enormous cosmic origami project. Here, spacetime isn't smooth or even loopy, it's a patchwork of tiny triangular blocks, glued together in a way that preserves cause and effect at every scale. The magic lies in the rules of assembly. Each triangle represents a chunk of spacetime with fixed edges and angles, snapping together like Lego bricks to form larger structures. But there's a crucial constraint: every connection must respect the flow of time. No bridges to the past, no sudden jumps to the future, just a rigid sequence where causes always precede effects. This causal requirement keeps the universe from devolving into chaos, ensuring that even at the quantum scale, the arrow of time points firmly forward. Where loop quantum gravity focuses on loops as the fundamental units, triangulations take a starkly different path. Think of it as comparing a knitted sweater to a geodesic dome. Both create structure, but one is flexible and interconnected, while the other relies on rigid, angular simplicity. This geometric approach sidesteps the infinite densities that plague classical physics by making spacetime granular, a bit like how pixelating an image prevents it from dissolving into blurry nonsense when you zoom in too far. But how do we test a theory written in geometry? Enter supercomputers. Researchers simulate universes by randomly assembling these spacetime triangles billions of times, letting the rules of quantum mechanics guide how they connect. Over time, large-scale structures emerge, and astonishingly, they often resemble the four-dimensional cosmos we recognize. It's as if by enforcing causality at the smallest scales, the simulation grows a universe that behaves like ours without anyone programming the big picture. Yet challenges remain. While simulations show promise, they struggle to incorporate matter and energy naturally, and some argue the rigid triangular building blocks are too simplistic, like trying to recreate the Sistine Chapel using only Duplo blocks. Still, the theory's stark elegance keeps physicists hooked. After all, if spacetime really is a geometric puzzle at heart, the answer to quantum gravity might not lie in hidden dimensions or vibrating strings, but in the timeless language of shapes and angles. What's truly fascinating is how this contrasts with other approaches. String theory seeks unity by adding complexity, extra dimensions, branes, multiverses. Triangulations do the opposite, peeling reality back to minimalist geometry. Neither has delivered a final answer, but together they remind us that the path to quantum gravity might not be a single road, but a sprawling web of possibilities, each one revealing a different facet of the universe's deepest secrets. What if gravity isn't fundamentally chaotic at the quantum scale? What if it just seems that way because we're missing a hidden pattern? That's the provocative promise of asymptotic safety, a theory so subtle that even many physicists overlook it. Unlike string theory's extra dimensions or loop quantum gravity's pixelated spacetime, this idea suggests gravity might play nice with quantum mechanics after all, if only we could see it from the right perspective. The key lies in an obscure corner of mathematics called renormalization group flow, which tracks how forces behave at different energy scales. Think of it like zooming in on a fractal. No matter how close you get, the pattern stays orderly. Proponents argue gravity might work the same way, appearing messy at everyday energies, but snapping into a predictable, finite pattern at extremes, like inside a black hole or at the Big Bang's first instant. The theory's roots trace back to Nobel laureate Gerard T. Hooft, who speculated in the 1970s that gravity could be safe from the infinities that usually plague quantum calculations. Decades later, physicists like Martin Reuter and Steven Weinberg built on this hunch, showing how gravity's mathematical equations might converge at high energies, like rivers merging into a single, stable flow. The magic happens when gravity's strength changes with energy in just the right way, balancing itself like a climber adjusting their grip on a sheer cliff. Too strong and quantum effects spiral out of control. Too weak and gravity vanishes from the picture entirely, but if it hits that Goldilocks zone, suddenly calculations that used to explode into nonsense yield clean, finite answers. Critics argue asymptotic safety is more mathematical hope than testable science, a clever trick with numbers that hasn't yet shown up in the real world. After all, the energies required to spot this safety are beyond anything we can create in a lab. Yet supporters point to tantalizing clues. Certain black hole properties and cosmic inflation models align eerily well with the theory's predictions. There's even speculation that the Higgs boson's mass, which seems unnaturally fine-tuned, might find an explanation here, as if gravity's high-energy behavior subtly tweaked the numbers behind the scenes. What makes this idea a dark horse candidate is its sheer economy. It doesn't demand extra dimensions, unseen particles, or rewrites of quantum mechanics. Instead, it suggests we've underestimated gravity's own flexibility, that it might tame itself when pushed to the limit. Imagine a wild stallion that, at full gallop, suddenly begins running in perfect geometric spirals. That's the dream of asymptotic safety, not a new physics but a hidden elegance in the physics we already have. Of course, elegance alone doesn't make a theory true. Without direct experimental proof, asymptotic safety remains a gorgeous hypothesis, a reminder that sometimes the universe's greatest secrets aren't found by adding complexity, but by looking deeper into what's already there. And if it's right, the most mysterious force in nature might turn out to be the most disciplined of all. What if gravity isn't a fundamental force at all, just a side effect of the universe's hidden chaos? That's the explosive idea behind emergent gravity, a theory that flips everything we thought we knew on its head. Erik Verlinde, a Dutch theoretical physicist, threw a wrench into modern cosmology when he proposed that gravity doesn't exist in the way Newton or Einstein imagined. Instead, it's an illusion, a force that bubbles up from something far stranger, the relentless march of disorder in the cosmos. Here's how it works. Think of empty space as a seething ocean of microscopic information, like a cosmic hard drive constantly shuffling bits. Every particle, every star, every galaxy disrupts this quantum soup, creating regions where entropy, the universe's tendency toward chaos, gets thrown off balance. And just like how heat flows from hot to cold, these entropy gradients generate what we perceive as gravity. It's not that mass bends spacetime, it's that mass changes the rules of the game for how information organizes itself. Suddenly, the apple falling from the tree isn't pulled by an invisible force, it's surfing a wave of microscopic disorder. This isn't just poetic metaphor. Verlinde's math borrows from holographic principles, the mind-bending notion that our three-dimensional universe might be a projection of data stored on a two-dimensional surface at its edge. If true, gravity would be like the shadow of that deeper information, processing a cosmic sleight of hand where the real action happens in a realm we can't see. But the wildest implication, emergent gravity might explain dark matter without needing dark matter at all. Astronomers have long assumed that invisible, mysterious stuff must exist to account for why galaxies rotate faster than predicted. But Verlin's equations suggest another answer. What if the extra pull isn't from unseen matter, but from the way entropy's hidden structure tugs on visible stars? Early tests are tantalizing. Some galactic rotation curves fit his predictions eerily well, though skeptics point out that other observations, like the bending of light around galaxy clusters, still seem to demand dark matter's presence. Critics argue emergent gravity is more philosophy than physics, a beautiful idea lacking the precision to replace Einstein's rigorously tested framework. Yet supporters counter that revolutions often start messy. After all, Newton's gravity was once just an apple's fall, and Einstein's relativity began as a thought experiment about chasing light beams. Maybe gravity, the force we thought we knew, is ready for its next great unmasking. The deeper question here isn't just about equations, it's about reality's layers. If gravity emerges from entropy, then what else might be hiding in the cosmic fine print? Could time or even consciousness itself be emergent phenomena, side effects of some vast, underlying computation we've yet to decipher? Verlin's theory doesn't just challenge textbooks, it whispers that the universe might be simpler and far weirder than we ever dared to dream. The idea that space and time might not just bend, but blur at the smallest scale sounds like science fiction, until you meet non-commutative geometry. This radical reimagining of spacetime doesn't just tweak Einstein's rules, it rewrites them with a mathematical twist so profound, even the order of events becomes uncertain. Imagine trying to navigate a city where left then forward doesn't lead to the same place as forward then left. That's the essence of non-commutativity. In this quantum realm, measuring position and momentum in one order gives a different result than reversing the steps, as if reality itself resists being pinned down. At the heart of this theory lies the work of Elaine Connes, a Fields Medal-winning mathematician who realized that if quantum particles can defy classical logic, why shouldn't spacetime? In the 1990s, Connes and his collaborators crafted a framework where coordinates no longer commute, meaning multiplying x by y isn't the same as y multiplied by x. The result, a universe where spacetime isn't a smooth stage but a fuzzy, quantum-like network of relationships, with uncertainty baked into its very fabric. It's as if the cosmos traded its rigid grid for an impressionist painting, where precise locations dissolve into probabilistic brushstrokes. But how does this abstract math connect to real physics? For when it offers a fresh path to unifying gravity with quantum mechanics, in Connes' model, the famous singularities that plague black holes and the Big Bang points where equations spit out infinities simply vanish. The fuzziness of non-commutative geometry acts like a quantum eraser, smoothing those sharp edges into something more manageable. Even the Higgs field, which gives particles mass, finds a natural home here, emerging from the geometry's inherent vibrations. Now the million-dollar question, could we ever detect this spacetime fuzziness? Some theories suggest it might subtly alter how high-energy particles travel. Gamma-ray bursts, those cosmic explosions billions of light-years away, could carry fingerprints of non-commutativity if their photons arrive at slightly different times based on energy. Others propose tabletop experiments with ultra-cold atoms, where quantum behavior at macroscopic scales might reveal hints of this hidden geometry. What's truly breathtaking is how non-commutative geometry reframes existence. If spacetime is fundamentally uncertain, then here and now aren't absolute truths but approximations, a cosmic compromise between our need to map the world and the universe's refusal to be neatly catalogued. It's a reminder that beneath the solid ground we walk on, the universe might be dancing to a far stranger rhythm. What if the universe isn't a continuous expanse of space and time, but more like a cosmic Lego set built from discrete, indivisible events stacked in a precise order? That's the radical premise of causal set theory, where reality isn't woven from loops or strings, but from elementary moments linked by cause and effect. Picture a vast growing network where every interaction, every particle collision, every photon's journey is a single dot in a sprawling web of relationships. These dots don't just float randomly, they're partially ordered, forming what mathematicians call a poset, where some events must precede others, creating an unbreakable chain of causality at the universe's core. This isn't just mathematical abstraction. The theory, championed by physicists like Raphael Sorkin, solves one of general relativity's biggest headaches: infinity. Black hole singularities and the Big Bang's infinitely dense starting point vanish in this framework, because you can't have an infinite number of events crammed into a finite volume if spacetime itself is fundamentally granular. It's like trying to fit an endless playlist into a vinyl record. There's only room for so many songs before you hit a hard limit. Here, the songs are spacetime's building blocks, ensuring physics never spirals into nonsensical infinities. But causal sets go deeper. By treating time as a sequence of discrete steps rather than a smooth flow, the theory resurrects an almost philosophical view of time's arrow, one where the future literally doesn't exist yet. Each new event is a fresh addition to the cosmic ledger, with causality acting as the glue that binds the universe's story together. No time travel paradoxes, no closed loops, just a strict no-cheating rule for cause and effect. It's a universe that respects the past's authority over the future, enforcing order at the most fundamental level. Where does gravity fit in? Surprisingly, it emerges from the network's structure. Picture ants navigating a labyrinth. The paths they take aren't dictated by some external force, but by the maze's twists and turns. Similarly, in causal set theory, what we perceive as gravity might just be the way matter and energy navigate the universe's underlying causal architecture. Massive objects warp this network, altering how events connect, and voila, you've got spacetime curvature without needing Einstein's smooth fabric. Yet for all its elegance, causal set theory faces hurdles. How do you derive the four-dimensional spacetime we see from these abstract event networks? Why does the large-scale universe look so smooth if it's fundamentally chunky? Some models suggest that randomness plays a role, like how a handful of thrown confetti can approximate a smooth curve if you step back far enough. Others propose dynamical algorithms where the poset grows in a way that mimics classical spacetime at cosmic scales. The real allure of causal sets lies in their minimalist beauty. Unlike theories that add hidden dimensions or unseen particles, this one strips reality down to its barest essentials: events and their causal links. It's a reminder that sometimes the most profound truths aren't found in complexity, but in the quiet order beneath the chaos, like finding the simple rules of grammar hidden in a novel's sprawling narrative. Whether causal sets hold the key to quantum gravity or merely illuminate part of the puzzle, they force us to ask: is the universe a story written in geometry, or a vast, unfolding chain of causes waiting to be decoded? What if the speed of light isn't the universe's ultimate speed limit after all? That's the daring proposition of Lifshitz gravity, a theory that tears up one of Einstein's most sacred rules to solve quantum gravity's biggest headaches. Named after physicist Peter Horava, this framework challenges Lorentz symmetry, the idea that the laws of physics stay constant no matter how fast or in what direction you're moving. Instead, it suggests that at super high energies, like those in the early universe or near black holes, time and space stop playing by the same rules. Time becomes stiffer, more rigid, while space gets stretchier, as if the cosmos itself has a built-in preference for how events unfold. The payoff: gravity suddenly becomes renormalizable, a technical term meaning its math stops spitting out infinities when you zoom into quantum scales. Think of it like smoothing out a crumpled piece of paper. By tweaking how time and space relate at tiny distances, Lifshitz gravity lets physicists calculate what happens inside singularities, or at the Big Bang, without their equations exploding into nonsense. It's as if the theory gives gravity a pair of quantum glasses, letting it see the world in sharp focus where before there was only blur, but the real magic happens in the early universe. Without strict Lorentz symmetry, inflation, the rapid expansion moments after the Big Bang, might not need exotic fields or fine-tuned initial conditions. Instead, spacetime's own asymmetry could have kick-started it naturally, like a coiled spring releasing energy as the cosmos cooled. Some models even suggest this could solve the Hubble tension, the puzzling mismatch in measurements of how fast the universe is expanding. If time flowed differently in the past, our cosmic yardsticks might need recalibrating. Critics, though, aren't sold. The theory requires meticulous fine-tuning to match everyday observations where Lorentz symmetry holds incredibly well. Others argue that breaking this symmetry unravels too much, like how removing one thread from a tapestry risks the whole image. There's also the ghost problem. Certain solutions predict phantom particles with negative probabilities, a clear red flag in quantum mechanics. Yet for all its controversy, Horava-Lifshitz gravity offers something rare: a workable quantum gravity candidate that doesn't need extra dimensions, hidden universes, or radical rewrites of quantum theory. It's a reminder that sometimes progress isn't about adding layers of complexity, but questioning the assumptions we never thought to challenge. And that raises a tantalizing thought: what other sacred rules of physics might be ripe for reimagining? What if the deepest truths of the universe aren't written in particles or forces, but in twisting threads of light? That's the visionary gamble of twistor theory, Roger Penrose's daring attempt to rebuild physics from the ground up using pure geometry. Forget spacetime coordinates or quantum fields. This framework imagines reality as a shimmering web of twistors, abstract mathematical entities that fuse energy, momentum, and spin into singular, luminous strands. Picture a beam of sunlight not as waves or particles, but as a helix of geometric information, spinning through a higher dimensional realm where light cones and quantum probabilities emerge from something far more primal. Penrose's brainchild, born in the 1960s, stands apart for its stark elegance, while string theory adds dimensions and loop quantum gravity chops spacetime into pieces. Twistors seek unity through subtraction. They strip physics down to its barest geometric essence, where even particles become secondary, mere shadows cast by the interplay of these twisty, luminous threads. The theory's most breathtaking insight, that quantum entanglement and the very structure of spacetime might share a common origin in twistor space, a domain where causality and locality dissolve into a tapestry of pure connection. It's as if Penrose found a hidden layer of the cosmic operating system, one where the code isn't written in numbers, but in spirals of light. Yet for all its beauty, twistor theory remains physics' best kept secret. Part of the challenge is its abstractness. Twistors live in a complex number landscape that makes string theory's Calabi-Yau manifolds look straightforward. Calculating something as mundane as an electron's path requires navigating this alien geometry like a cosmic sailor charting stars in 6 dimensions. But when it works, the results are uncanny. Twistor methods have cracked problems in quantum field theory that stump traditional approaches, especially in modeling particle scattering amplitudes. It's as if these twisty threads know shortcuts through reality's math that our conventional tools keep missing, the theory's most radical implication. That spacetime itself might be an illusion, a derivative construct that only emerges when we zoom out from twistor space's intricate weave. Imagine watching a movie and suddenly realizing the plot only makes sense because millions of pixels align just so. Twistors suggest our experience of space and time might be that kind of collective mirage. Even black holes get a makeover. Their event horizons could form from twistor networks so dense they twist back on themselves, trapping information in knots of pure geometry. So why hasn't twistor theory taken center stage? Beyond its mathematical intensity, it struggles with gravity's full incorporation, while it handles quantum fields with grace, marrying twistors to Einstein's general relativity. remains an open challenge one Penrose and his collaborators continue to chip away at. Yet its influence quietly permeates physics, inspiring breakthroughs from holography to quantum computing. Like a conceptual beacon, it reminds us that sometimes the path forward isn't through brute force complexity, but through returning to the simplest questions with fresher eyes. After all, if the universe began with a singularity, maybe its truest description isn't a cacophony of equations, but a single radiant twist. Imagine a universe where every particle we know, electrons, quarks, photons, has a secret twin, a mirror image lurking just beyond our perception. That's the elegant promise of supersymmetry, a theory so mathematically beautiful it once seemed inevitable. These hypothetical twins, dubbed sparticles, short for superparticles, would balance the quantum scales in a way that makes gravity's unruly behavior suddenly tractable. For decades, physicists dreamed that smashing protons together at CERN Large Hadron Collider would unveil this hidden family, proving that nature adores symmetry not just in snowflakes or galaxies, but at the most fundamental level. Supersymmetry, or SUSY for short, doesn't just tidy up the particle zoo, it offers a lifeline to quantum gravity. Here's why: in the Standard Model, gravity remains the stubborn outsider because the graviton, its hypothetical force carrier, resists playing nice with quantum rules. But in a supersymmetric world, every sparticle's spin and energy would counterbalance the infinities that plague gravity's equations, like a cosmic accounting trick where the books finally balance. Even better, the lightest particle could be dark matter, solving two cosmic mysteries with one elegant twist. Then came the LHC's silence. After years of collisions at unprecedented energies, not a single sparticle materialized. The thresholds where theorists predicted SUSY appearance, energies that would have made these twins just heavy enough to evade earlier detection, came and went without a whisper. For many it was a gut punch, the dream of a naturally balanced universe where gravity and quantum forces harmonized effortlessly, began to fray. Yet supergravity, SUSY ambitious cousin that grafts these symmetries onto spacetime itself, never fully surrendered. While the LHC's null results forced physicists to rethink SUSY's simplest forms, supergravity's mathematical machinery kept churning out insights. In higher dimensions or more complex configurations, SUSY might still hide, its particles so massive they'd require colliders the size of Saturn's rings to produce. Others argue SUSY could manifest not as particles, but as organizing principles shaping the early universe's inflation or black hole entropy. What keeps theorists clinging to these ideas isn't just stubbornness, it's the unnerving elegance they bring to physics' biggest puzzles. Without SUSY, the Higgs boson's mass becomes bizarrely fine-tuned, as if the universe won a lottery with odds of 1 in a billion. Supergravity, meanwhile, remains string theory's most fertile playground, the only framework where gravity's quantum version emerges without infinite headaches. Even if nature skipped the sparticle buffet, the math behind these theories continues to reveal hidden connections. Like a Rosetta Stone for cosmic codes we're still learning to read. So is supersymmetry dead? Not quite. It's evolved from a hopeful prediction to a provocative what if, a reminder that sometimes the universe's deepest truths aren't found in the collisions we observe, but in the symmetries we dare to imagine. And that leaves us with a tantalizing thought: if sparticles aren't the answer, what other cosmic bookkeepers are out there, waiting to balance gravity's ledger? Entropic gravity isn't just about redefining how mass bends spacetime, it's about asking whether gravity even exists as a force at all. Eric Verland's theory doesn't just tweak the rules, it suggests we've been misreading the cosmic rulebook entirely. Picture a crowded dance floor where everyone moves in sync, not because some invisible hand directs them, but because the music, the underlying entropy of the system, nudges them toward chaos. In Verland's universe, gravity is that emergent rhythm, a side effect of the universe's relentless drive toward disorder. This isn't just philosophical sleight of hand. The math behind entropic gravity borrows from black hole thermodynamics, where the famous Bekenstein-Hawking formula ties a black hole's entropy to its surface area. Verlin took this a step further. If entropy governs the most extreme objects in the cosmos, why not everything else? His equations describe gravity as a kind of entropic force, like the pressure that pushes a piston when gas molecules randomize their motion. Except here the gas is the hidden information encoded in spacetime itself, and the pressure is what we call gravity, but the real bombshell came when Verlin applied this to galaxies. Astronomers have long assumed dark matter must exist because stars orbit galactic centers faster than visible mass can explain. Entropic gravity offers a radical alternative. What if there's no dark matter at all? Instead, the extra pull could come from the way visible matter distorts the underlying entropy field, like a rock creating ripples in a pond. Early studies of low surface brightness galaxies, faint, diffuse systems where dark matter's grip should be obvious showed uncanny alignment with Verlin's predictions. It was as if the cosmos whispered, maybe you've been missing the point all along, yet not everyone's convinced. Recent analyses of galaxy clusters, enormous structures where hundreds of galaxies swarm together, paint a murkier picture. When teams mapped how these clusters bend light via gravitational lensing, the distortions often matched dark matter models better than entropic gravity's predictions. Critics argue that Verlin's framework, while elegant, struggles to explain all the data without ad hoc tweaks. It's like having a key that fits some locks but jams in others, promising, but not yet master of all doors. The debate gets even thornier when you zoom out to cosmology's biggest puzzles. Dark energy, the mysterious force accelerating the universe's expansion, finds no natural home in entropic gravity yet. Some theorists propose tweaks like treating the cosmological constant as an entropy gradient, but these ideas remain speculative. Meanwhile, lab experiments trying to detect entropy's microscopic fingerprints, like subtle temperature fluctuations near massive objects, have yet to deliver smoking gun results. What keeps entropic gravity in the game isn't just its potential to kill two birds, dark matter and quantum gravity, with one stone, it's the way it reframes our place in the cosmos. If gravity emerges from information, then the universe isn't a machine governed by rigid laws, it's a kind of quantum computer, constantly processing and reorganizing its own data. Black holes become cosmic hard drives, galaxies as swirling patterns in the code, and us, maybe we're just fleeting patterns in the noise, the universe's way of observing itself. That's the real revolution here, not just a new theory of gravity, but a whole new metaphor for reality, one where the forces we thought fundamental might just be the universe's way of keeping its own books. Whether Verlin's vision holds up or not, it's already done something remarkable, reminded us that sometimes the most profound breakthroughs begin by questioning not the answers, but the questions themselves. What if our three-dimensional universe, with all its galaxies, stars, and planets, is nothing more than an illusion, a holographic projection cast from a two-dimensional surface at the edge of reality? This isn't science fiction, it's the holographic principle, a theory so radical it rewrites the rules of space itself. The idea first took root in the study of black holes, those cosmic anomalies where gravity is so strong that even light can't escape. When physicists Stephen Hawking and Jacob Bekenstein discovered that a black hole's entropy, its measure of disorder, was proportional to its surface area, not its volume, it sparked a revolution. How could the information inside a black hole be encoded on its surface, like a cosmic DVD encoding a three-dimensional movie on a flat disk? Leonard Susskind and Gerard T. Hooft took this paradox and ran with it. If black holes store their secrets on a 2D boundary, they argued, maybe everything does. The holographic principle was born, the mind-bending proposal that all the information in our universe, every particle, every force, even your thoughts right now, could be written on a distant, two-dimensional surface we'll never see. It's as if reality is a shadow play, with the true actors lurking just off stage. This isn't just poetic metaphor. The math behind it, known as ADS/CFT duality, is one of the most fertile tools in theoretical physics. Imagine a hypothetical universe with negative curvature, an anti-de Sitter space where light rays curve inward instead of outward. In this strange cosmos, the duality suggests that a theory of gravity playing out in the 3D bulk can be perfectly mirrored by a quantum field theory living on its 2D boundary, like a flawless reflection in a cosmic funhouse mirror. Suddenly, the messy quantum behavior of particles in our world could be the flip side of a simpler, gravity-free calculation happening in a lower dimension. The implications are staggering. If true, the holographic principle would mean that spacetime itself isn't fundamental, it's emergent, a byproduct of some deeper, information-based reality. Black holes aren't destroying information, they're scrambling it onto their event horizons, like celestial archivists preserving data in a format we don't yet understand. Even the Big Bang might not have been a fiery explosion in space, but a quantum computation unfolding on a hidden 2D screen. But how do we test something this abstract? Surprising clues come from plasma physics and superconductors. Certain lab-created materials, when cooled to near absolute zero, exhibit behavior that mirrors predictions of ADS/CFT duality, as if the universe is teasing us with glimpses of its underlying code. Others hunt for anomalies in the cosmic microwave background, subtle fingerprints of a holographic imprint left over from the universe's infancy. Skeptics argue the principle, while mathematically elegant, remains trapped in hypothetical toy models. Real cosmology doesn't resemble anti-de Sitter space. Our universe is expanding at an accelerating rate, not curling inward, yet proponents counter that the core insight, the primacy of information over geometry, might transcend the specific math, offering a new lens to view quantum gravity altogether. What's truly humbling is the scale of the idea. If the holographic principle is right, then every star you've ever seen, every planet you've walked on, even your own consciousness, might just be pixels in a cosmic projection. The universe isn't a stage, it's the shadow of a stage, and we're all part of the performance. The question then becomes, who or what is casting the light? What if the smooth, continuous universe we experience is actually a vast shifting network, flickering between connections like a cosmic game of connect the dots? That's the startling vision of quantum gravity, a theory where spacetime isn't woven from loops or strings, but from a dynamic web of quantum bits that can switch relationships on and off. Imagine trillions of tiny nodes, each representing the most basic unit of reality, with links between them constantly forming and breaking like neural pathways in some gargantuan cosmic brain. In this model, the vacuum of space isn't empty at all. It's a frenetic dance of potential connections waiting to be activated. The theory's name isn't just wordplay. Gravity comes from the mathematical term for networks of connected points, while quantum refers to the unpredictable, probabilistic nature of these connections. At the universe's birth, this network might have been completely frozen, a rigid crystalline structure where no information could flow. Then, as the cosmos cooled, links began to thaw, allowing nodes to communicate and creating what we now perceive as spacetime. It's like watching ice melt into water. The transition from a static grid to a fluid medium could explain cosmic inflation's explosive expansion in the early universe. Suddenly, the Big Bang's rapid growth isn't a mysterious force acting on space, it's space itself unlocking, link by link, but quantum gravity doesn't stop there. It could also solve one of physics' oldest puzzles, why the speed of light is constant. In this framework, light's speed isn't some fundamental limit, it's simply the maximum rate at which information can hop between connected nodes. Think of it like a game of telephone across the cosmos. A photon isn't racing through space so much as being passed along a chain of quantum handshakes. with each step constrained by the network's architecture. This explains Einstein's famous postulate without invoking any mysterious cosmic speed limits, just the natural rhythm of a universe built from relationships rather than distances. Where the theory gets truly radical is in its treatment of black holes. At their event horizons, the network's connections might stretch and thin like a fraying rope, distorting the flow of information until it effectively stops. No singularities, no infinities, just a region where the cosmic graph's nodes become isolated, freezing time itself from the perspective of an outside observer. Even dark energy could find an explanation here. If the network keeps forming new links over time, this steady rewiring might manifest as the accelerating expansion we observe today. Testing quantum gravity isn't easy, but physicists have clever workarounds. Some study high-energy gamma rays for subtle delays in their arrival times, hints that spacetime's network might process different energies at slightly different speeds. Others simulate graph-like structures in supercooled quantum materials, watching how excitations move through artificial lattices that mimic the theory's predictions. There's even speculation that gravitational wave detectors could spot anomalies in spacetime vibrations, like echoes from the cosmic graph's underlying structure. What makes quantum gravity so compelling isn't just its solutions, it's the philosophy beneath them. Reality isn't a stage with actors moving across it. The stage is the actors, constantly redefining themselves through interaction. It's a universe where existence itself is relational, where here and there only make sense because particles agree to talk to each other, and if that's true, then the fabric of reality might be far more malleable and far more strange than we ever suspected. What if spacetime isn't just stitched together like a tapestry, but more like a cloud condensing from droplets in the air? That's the striking vision of group field theory, a framework that takes the quantum loops of loop quantum gravity and merges them with the abstract power of tensor models. Here, the universe isn't just made of tiny loops, it's a fluid, dynamic condensate of even more fundamental building blocks, swirling and clumping until the familiar fabric of reality emerges. Picture billions of microscopic Lego pieces, each carrying a scrap of geometric information, floating in a primordial soup. Under the right conditions, these pieces snap together, not into rigid structures but into a shimmering collective state, a cosmic phase transition where spacetime itself materializes from chaos. The magic lies in the math. Group field theory borrows techniques from quantum field theory, but instead of fields spread across space, it deals with fields of geometry, mathematical entities that dictate how those abstract building blocks connect. Think of it like a cosmic recipe where the ingredients aren't particles or forces, but relationships. When these relationships reach a critical density, they undergo condensation, much like steam turning into water. Suddenly, the froth of disconnected quanta locks into a coherent structure, giving birth to space and time as we know them. This isn't just elegant abstraction. The theory tackles one of quantum gravity's toughest riddles: how to bridge the gap between the quantum microworld and the smooth spacetime of general relativity. In group field theory, the transition isn't forced, it's natural. At high energies like those near the Big Bang, the condensate evaporates, revealing the boiling quantum foundations beneath. But as the universe cools, geometric order crystallizes, much like ice forming on a pond. Even black holes find a fresh interpretation. Their event horizons might mark regions where the condensate frays, thinning out until spacetime's underlying turbulence peeks through. Critics argue the theory is still in its infancy, with equations so complex they make string theory look like child's play, yet its potential is staggering. Some models suggest spacetime could have phases, like matter transitioning between solid, liquid, and gas. Could there be regions of the cosmos where spacetime melts back into its primordial soup? Others explore how quantum fluctuations in the condensate might seed cosmic inflation, offering a new angle on the universe's explosive birth. What makes group field theory so gripping isn't just its answers, it's the way it reframes the question. Instead of asking how gravity behaves at quantum scales, it asks, what if gravity isn't fundamental at all? If spacetime condenses from simpler ingredients, then the forces we call universal might just be emergent habits, patterns etched into the universe's quantum substrate. It's a reminder that sometimes the deepest truths aren't hiding in the equations we've written, but in the ones we've yet to imagine. Black holes aren't just cosmic vacuum cleaners, they're the universe's most enigmatic thermometers. Back in the 1970s, a young physicist named Jacob Bekenstein made a radical suggestion. What if black holes, those regions of spacetime where gravity is so strong even light can't escape, aren't just simple gravitational traps? What if they have temperature? At first, even Stephen Hawking dismissed the idea. How could something that devours everything, leaving no trace behind, behave like a warm cup of coffee? But Hawking soon realized Bekenstein was onto something monumental. When he crunched the numbers, he found black holes do radiate energy, slowly leaking particles now famously known as Hawking radiation. This wasn't just a quirky prediction, it was the first concrete bridge between gravity, quantum mechanics, and thermodynamics. The implications were staggering. If black holes have temperature, they must also have entropy, a measure of disorder. But here's the twist: Bekenstein and Hawking showed a black hole's entropy isn't proportional to its volume, as you'd expect for ordinary objects. Instead, it's tied to the surface area of its event horizon. Imagine scribbling every bit of information that ever fell into a black hole, not on pages stuffed inside it, but in its outer shell, like a cosmic scratchpad. This revelation birthed the holographic principle, the idea that our three-dimensional universe might be a projection of data stored on a two-dimensional boundary. Quantum gravity wasn't just about particles or spacetime, it was about information. Yet Hawking radiation opened a Pandora's box of paradoxes. If black holes evaporate over eons, what happens to all that swallowed matter? Quantum mechanics insists information can't be destroyed, but black holes seem to erase it permanently. This information loss paradox set off decades of debate, culminating in an even stranger idea, the firewall paradox. Imagine falling toward a black hole's event horizon. According to Einstein, you'd feel nothing special, just a quiet drift into darkness, but quantum mechanics suggests something far more violent. As Hawking radiation leaks out, it could create a searing wall of energy at the horizon, incinerating anything crossing it. Two flawless theories, one brutal contradiction. Firewalls force us to confront the messy marriage of quantum mechanics and gravity. Some physicists argue their proof Einstein's smooth spacetime breaks down at quantum scales, revealing a chaotic substructure. Others propose wild workarounds like fuzzballs, black holes with no interiors at all, just tangled strings of quantum information. Then there's the ER=EPR conjecture, suggesting entangled particles might be connected by microscopic wormholes, weaving quantum weirdness into spacetime's fabric. The beauty of black hole thermodynamics isn't just in the answers, it's in the questions. By studying how these cosmic monsters radiate, vanish, and maybe even preserve information, we're not just decoding gravity. We're learning how the universe remembers. Every photon Hawking radiation steals from a black hole might carry a scrambled fragment of its history, like pages torn from a book but still legible if you know how to assemble them. That's the true gift of Bekenstein and Hawking's work. They turned black holes from cosmic dead ends into Rosetta Stones for quantum gravity. The firewalls and paradoxes aren't roadblocks, they're signposts, pointing toward a deeper layer of reality where information, spacetime, and quantum mechanics finally reconcile. The question now isn't whether black holes hold the key, but how many locks we'll need to turn before the door swings open. Einstein's theory of relativity has reigned supreme for over a century, treating space and time as a smooth, continuous fabric where the speed of light is the ultimate cosmic speed limit. But what if that's only part of the story? What if, at the tiniest scales of the universe, there's another limit not just on speed, but on length itself? That's the provocative idea behind doubly special relativity, a theory that dares to tweak Einstein's masterpiece by introducing a minimum measurable distance into the fabric of reality. Imagine a universe where you can't zoom in indefinitely, where spacetime itself has a kind of resolution limit, like a digital image that blurs when you magnify it too far. This isn't just abstract speculation. The theory emerged from a simple but profound question: if quantum gravity suggests spacetime might be granular at the Planck scale, a distance so small it makes an atom look gargantuan, why doesn't relativity account for that? In the early 2000s, physicists like Giovanni Emiliano Camiglia proposed a radical fix: modify Einstein's equations to include not just the speed of light as a constant, but also the Planck length as an unbreakable lower bound. The result: a universe where the rules of relativity hold, but only up to a point. Beyond that, the very concepts of here and there start to blur, and the energy of a particle can warp how it perceives distances, like a cosmic funhouse mirror that distorts differently for every observer. One of the most tantalizing predictions of doubly special relativity involves gamma-ray bursts, those colossal explosions that fling high-energy photons across billions of light-years. If spacetime has a minimum length, then photons of different energies might experience it slightly differently. Picture two runners racing through a field, one on smooth pavement, the other through tall grass. Even if they're equally fast, the one battling resistance will lag. Similarly, in this framework, higher energy gamma rays could interact more strongly with spacetime's granularity, slowing their journey by a fraction of a second compared to lower energy light. It's a minuscule effect, but over cosmic distances, those delays could add up and astronomers might spot them. Some detectors, like the Fermi Gamma Ray Space Telescope, have hunted for these delays in bursts from the distant universe. A few candidates have shown hints of the expected energy-dependent lag, though the data isn't conclusive yet. Skeptics argue these delays could stem from other sources, like the burst's own chaotic physics. But supporters counter that if the effect is real, it would be the first observational whisper of spacetime's quantum structure, a clue that relativity, for all its brilliance, might need a subtle upgrade. Doubly special relativity isn't just about rewriting textbooks, it's a bridge, a stepping stone between the familiar world of Einstein and the uncharted territory of full quantum gravity. Unlike theories that scrap relativity entirely, this one seeks to gently extend it, preserving its core while accommodating the Planck scale's mysteries. That makes it a rare compromise in a field often torn between revolution and tradition, yet the theory isn't without its critics. Some argue that introducing a minimum length breaks Lorentz invariance, the sacred principle that physics should look the same to all observers, no matter their speed. Others note that the math becomes fiendishly complex when you try to merge this idea with gravity itself, but its proponents see these challenges as growing pains. After all, Einstein's relativity once seemed incompatible with Newton's gravity, until it wasn't. What makes doubly special relativity so compelling isn't just its potential to solve puzzles. It's the philosophical shift it represents, the recognition that even our most cherished theories might be approximations, waiting to be refined by the universe's deeper layers. Whether it's a final answer or just a signpost pointing toward one, it reminds us that the quest for quantum gravity isn't about overthrowing Einstein, it's about listening to what he might have missed. And sometimes the loudest whispers come from the smallest scales. In Einstein's universe, time is a rigid scaffold, an unchanging backdrop against which the cosmic drama unfolds. But what if time isn't absolute at all? What if it's more like a rubber band, stretching and compressing depending on how you look at it? That's the radical proposition of shape dynamics, a theory that doesn't just tweak general relativity, it reimagines gravity from the ground up by stripping away time's privileged status and replacing it with something far more fluid, pure shape. At its core, shape dynamics trades Einstein's spacetime geometry for conformal geometry, a framework where angles matter, but distances and durations don't. Think of it like a cosmic game of telephone, where the universe only cares about the relationships between objects, not the absolute space separating them. In this view, a star's gravitational pull isn't about warping some pre-existing stage, it's about how all the actors in the cosmic play adjust their positions relative to one another, with no director shouting cues from offstage. Time becomes emergent, a side effect of these shifting configurations rather than a master clock ticking in the background. This isn't just mathematical whimsy. Shape dynamics tackles one of quantum gravity's thorniest problems, the problem of time. In quantum mechanics, time is external, a parameter that flows uniformly while systems evolve. But in general relativity, time is dynamic, bending and twisting with gravity. When the two theories collide, time becomes a schizophrenic concept, neither fish nor fowl. Shape dynamics cuts the knot by eliminating time as a fundamental entity altogether. Instead, change is measured purely by how the universe's shapes rearrange, like tracking a dancer's movements without ever glancing at the clock. The theory's elegance lies in its symmetry. Just as a sphere looks identical no matter how you rotate it, shape dynamics suggests the universe's laws remain unchanged under conformal transformations, stretching, squeezing, or rescaling space without altering the underlying physics. This symmetry could explain why the cosmos appears so finely tuned for structure. If the universe only cares about angles and proportions, not absolute scales, then the delicate balance allowing galaxies and life to form might not be luck, but inevitability. Critics argue shape dynamics struggles to replicate all of general relativity's successes, like predicting the precise orbit of Mercury or the bending of light around the Sun. Yet proponents point to tantalizing overlaps with other quantum gravity candidates. Some versions of loop quantum gravity, for instance, naturally incorporate conformal symmetry, hinting at a deeper connection. There's even speculation that shape dynamics could resolve the black hole information paradox, treating the event horizon not as a destructive boundary, but as a surface where conformal relationships reconfigure, preserving information like a cosmic recycler. What's truly transformative about shape dynamics isn't its math, it's the philosophical shift. If time isn't fundamental, then our perception of its flow might be as illusory as the flat Earth beneath our feet. The universe doesn't happen, it configures moment by moment with no past or future, just an endless now rearranging itself. It's a vision both humbling and exhilarating, reminding us that sometimes the key to progress isn't adding new layers of complexity, but daring to peel back the ones we thought were sacred. What if the universe isn't just painted in shades of gray, but in a full, shimmering rainbow? That's the dazzling premise of rainbow gravity, a theory that suggests spacetime isn't a one-size-fits-all fabric, it's a dynamic, energy-dependent prism where particles of different energies experience different realities. Imagine tossing a red marble and a blue marble into a pond. In our everyday world, they'd ripple outward at the same speed, but in rainbow gravity's cosmos, the blue marble representing a high-energy particle like a gamma ray might zip through spacetime faster than its red counterpart, as if the very ground beneath them has shifted. The theory's roots trace back to a simple but radical question: why should the speed of light be universal if spacetime itself might have a quantum structure? In the early 2000s, physicists like Giovanni Emiliano Camiglia and Lee Smolin proposed that at ultra-high energies, like those near the Big Bang or inside black holes, the fabric of reality could stretch and compress depending on a particle's energy. This isn't just a tweak to Einstein's relativity, it's a full repainting. The familiar smooth spacetime of general relativity becomes a rainbow metric, where each color energy level gets its own version of gravity's rules. Here's where it gets wild. If rainbow gravity is real, the cosmic speed limit isn't just the speed of light, it's a spectrum of limits. Photons from distant gamma-ray bursts, which span a range of energies, might arrive at Earth at slightly different times after racing across the universe. High-energy photons could outpace their lower-energy siblings, like sprinters on an invisible, energy-warped track. Some telescopes have even hunted for these delays in burst data, though the results remain tantalizingly inconclusive. Skeptics argue that other astrophysical effects could mimic the signal, but supporters counter that the patterns align eerily well with rainbow gravity's predictions. Yet the theory isn't just about speed, it could redefine black holes entirely. In rainbow gravity, a black hole's event horizon might not be a fixed boundary, but an energy-dependent illusion. A high-energy particle could zip right through what low-energy observers see as an inescapable trap, like a ghost slipping through walls. Even the Big Bang transforms. Instead of a singular explosion from nothingness, the early universe might have been a frothing sea of energy-dependent spacetimes, each color vibrating to its own quantum tune until they harmonized into the cosmos we know. The biggest hurdle, experimental proof. Rainbow gravity's effects are subtle at everyday energies, like trying to hear a whisper in a hurricane, but physicists are resourceful. Some hunt for anomalies in ultra-high energy, cosmic rays of particles with energies 1,000,000 times greater than anything our colliders can produce. Others simulate rainbow-like spacetime in lab-grown quantum materials, where electrons behave as if they're navigating an energy-warped geometry. What makes rainbow gravity so compelling isn't just its audacity, it's the way it reframes our place in the cosmos. If spacetime bends differently for different energies, then reality isn't a single stage, but a layered performance where each observer's energy dictates their script. It's a universe that doesn't just tolerate diversity, it's built from it. And that raises a hauntingly beautiful thought. What if the cosmos we see is just one slice of a far richer, far stranger spectrum, waiting beyond the limits of our perception? Quantum Einstein gravity sounds like a contradiction at first. How do you take the rock-solid equations of general relativity and smash them together with the fuzzy uncertainty of quantum mechanics? This theory doesn't just attempt a merger, it re-engineers gravity from the ground up using a powerful mathematical tool called the renormalization group. Picture a sculptor refining a block of marble, not by adding clay, but by chiseling away imperfections at every scale until the true form emerges. That's what renormalization does. It peels back layers of energy and distance, revealing how gravity's strength might shift depending on where and how closely you look. At cosmic scales, quantum Einstein gravity flexes its muscles beautifully. The theory suggests gravity weakens at extremely high energies, near the Big Bang or inside black holes, acting like a cosmic pressure valve that prevents singularities from forming. Instead of an infinitely dense point at the universe's birth, you'd get a quantum bounce, where space-time rebounds like a compressed spring. This elegantly sidesteps the need for exotic inflation fields, offering a natural explanation for why the universe is so startlingly uniform. Even dark energy finds a plausible home here, not as some mysterious substance, but as a side effect of gravity's quantum corrections over billions of years. But the cracks appear when this framework shakes hands with particle physics. While it tames gravity's quantum chaos, it struggles to reconcile with the Standard Model's meticulously tested particles. The Higgs boson's mass, for instance, becomes a puzzle again. Without supersymmetry or extra dimensions, quantum Einstein gravity can't explain why it's so light compared to the Planck scale. There's also the specter of ghost particles, mathematical artifacts that haunt the equations with negative probabilities, threatening to unravel the theory's internal consistency. Yet its proponents aren't backing down. They argue these hurdles might reflect our incomplete understanding, not the theory's flaws. Some explore hybrid models where quantum Einstein gravity partners with string theory or loop quantum gravity, like rival architects collaborating on a bridge neither could build alone. Others hunt for smoking gun signatures in gravitational waves or the cosmic microwave background, subtle imprints that could betray gravity's quantum adjustments to Einstein's original blueprint. What makes this approach so compelling is its refusal to surrender Einstein's core insight that gravity is geometry while daring to redraw the lines where needed. It's not a revolution, but a renovation, preserving the house of relativity while reinforcing its foundations for the quantum storms ahead. Whether it's the final answer or just a stepping stone, quantum Einstein gravity reminds us that sometimes progress isn't about tearing down the old, but learning how to rebuild it stronger. Spacetime isn't just curved, it might be faceted, like a cosmic diamond cut into countless geometric shards. That's the striking vision of Simplicial quantum gravity, where the smooth continuum of Einstein's universe gets replaced by a vast mosaic of higher dimensional triangles called simplices. Picture gluing together tetrahedrons, the 3D cousins of triangles, to approximate the contours of a sphere. Now imagine doing that in 4 dimensions, with spacetime itself as the shape you're assembling. Each simplex becomes a tiny building block of reality, their flat faces snapping together to create the illusion of curvature, like a digital mesh rendering the curves of a video game character. This isn't just abstract math. The theory owes its roots to Reg calculus, a brilliant workaround developed by physicist Tullio Reg in the 1960s. Frustrated by the computational nightmare of solving Einstein's equations for complex geometries, Reg realized you could sidestep the problem entirely by approximating spacetime as a network of interconnected simplices. Instead of wrestling with differential equations at every point in space, you'd calculate gravity's effects by summing over the angles and lengths of these geometric pieces, like calculating a mountain's volume by counting the cubes in a 3D model. The result? A discrete, computable version of general relativity where spacetime's wrinkles emerge from the way these blocks fit or don't fit together. Simplicial quantum gravity takes Reg's insight and turbocharges it for the quantum era. Here, the simplices aren't just static approximations, they're dynamic, quantum entities that fluctuate and rearrange. Think of spacetime as a cosmic Lego set where the bricks constantly snap apart and reconnect, governed by probabilities rather than rigid classical rules. In this framework, black holes might form when simplices cluster into ultra-dense configurations, while the Big Bang could represent a phase transition where the entire network reconfigured itself, like ice melting into water. Even dark energy finds a geometric interpretation. If the average gap between simplices grows over time, the universe's expansion could emerge naturally from the lattice's stretching. The real power of this approach lies in its computational elegance. Unlike string theory's tangled extra dimensions or loop quantum gravity's abstract networks, simplicial gravity lends itself to brute force number crunching. Supercomputers can simulate universes by gluing together millions of simplices, tweaking their connections, and watching spacetime's large-scale properties emerge, a bit like training a neural network to recognize cats by feeding it endless photos. These simulations have already shed light on quantum foam, the hypothesized turbulent structure of spacetime at the Planck scale. Some models even suggest spacetime might undergo phase changes, flipping from one geometric flavor to another under extreme conditions, like steam condensing into droplets. Yet puzzles remain. How do you guarantee these faceted approximations recover Einstein's smooth spacetime at everyday scales? Some solutions invoke randomness. If the simplices are small and numerous enough, their jagged edges blur into continuity, like pixels vanishing into a high-res image. Others propose dynamical rules that drive the network toward classical behavior as it grows, akin to how individual water molecules conspire to create a still pond surface. Critics also note the theories struggle to incorporate matter naturally. While it models gravity beautifully, particles and fields still feel like guests crashing a geometric party. What makes Simplicial quantum gravity so compelling isn't just its practicality, it's the philosophical shift it embodies. Spacetime isn't handed to us pre-made, it's assembled, piece by piece, from simpler ingredients. The universe isn't a painting, but a mosaic, and every star, every atom, might just be a pattern in its shimmering, ever-shifting tessellation. Whether this approach ultimately holds the key to quantum gravity or merely illuminates part of the path, it reminds us that sometimes the most profound truths are hiding in plain sight, not in equations scribbled on a blackboard, but in the timeless language of shapes. Matrix models strip string theory down to its bare essentials, like a master chef reducing a complex sauce to reveal its core flavors. These are not the full, 10-dimensional symphonies of traditional string theory, but minimalist jazz improvisations, tight mathematical frameworks where strings vibrate in just 1 or 2 dimensions instead of the usual 10. At first glance, this seems too simple to describe gravity, let alone black holes, but here's the twist: sometimes less really is more. By constraining strings to lower dimensions, matrix models paradoxically unlock profound insights into how spacetime and gravity emerge from deeper, quantum structures. The magic happens when you realize these models aren't just playing with fewer dimensions, they're simulating how strings behave in highly curved, extreme environments like black hole horizons. Take the so-called BFSS matrix model, named after its creators Banks, Fischler, Schenker, and Susskind. It describes a universe where strings are represented not as wiggly lines but as matrices, grids of numbers whose interactions encode the dynamics of gravity. Think of it like translating a novel into Morse code. The format changes, but the story remains intact. In this case, the story is how black holes store information. The matrices' chaotic, overlapping interactions mimic the frenetic scrambling of data at a black hole's event horizon, offering a toy universe where information paradoxes become tractable puzzles rather than unsolvable riddles. Then there's the holographic connection. Matrix models thrive in lower dimensions, but their solutions often describe physics in higher dimensional spaces, a hallmark of holography, where a theory on a boundary encodes the bulk of a higher dimensional world. It's as if these models are whispering a secret. Gravity isn't fundamental, but a shadow cast by quantum processes playing out on a distant, lower dimensional surface. This isn't just philosophy, it's math with teeth. For instance, certain matrix models precisely reproduce the entropy of black holes predicted by string theory, matching Bekenstein and Hawking's iconic calculations without ever invoking general relativity directly. What's startling is how these stripped-down models tackle problems that baffle full string theory. Take the black hole information paradox. In matrix models, information never truly vanishes, it just gets tangled in the matrices web, eventually re-emerging as radiation. The math suggests black holes aren't cosmic shredders but chaotic, giant quantum computers, churning data until it resurfaces in garbled but recoverable form. It's a vision that even Hawking eventually came to accept, though he famously bet against it early on. Yet matrix models aren't without limits. They excel at probing specific regimes like black holes in certain types of universes, but struggle to describe the full richness of our cosmos. Critics argue they're too simplistic, like trying to reconstruct a rainforest from a single fern, but supporters counter that sometimes you need the fern to understand the forest. By isolating gravity's essence in controlled settings, these models act as laboratories for ideas too complex to simulate elsewhere. When supercomputers crunch matrix model equations, they're not just solving abstract math, they're stress testing the very foundations of holography and quantum gravity. The real lesson here isn't just about matrices or strings, it's about the power of simplification in science. Just as Einstein imagined chasing a light beam to uncover relativity, matrix models remind us that progress often comes not from adding complexity, but from daring to subtract it. Whether they are the final key to quantum gravity or just a stepping stone, they prove one thing: sometimes the universe's deepest truths hide not in the noise, but in the silence between the notes. What if gravity seems weak not because it's inherently feeble, but because most of it is hiding in another dimension? That's the spine-tingling premise of Randall-Sundrum models, where our familiar three-dimensional universe floats like a delicate membrane, a brain, within a higher dimensional space teeming with gravitational forces we can barely perceive. Imagine living on the surface of a pond, oblivious to the crushing depths below. To you, water might seem shallow and gentle, but dive deeper and the pressure becomes immense. In this theory, gravity isn't diluted, it's just concentrated somewhere we can't reach. The idea sprang from one of physics' most embarrassing puzzles, the hierarchy problem. Why is gravity so absurdly weaker than the other fundamental forces? A magnet can lift a paperclip, defying Earth's entire gravitational pull with ease. The math suggests gravity's feebleness demands either bizarrely precise fine-tuning like balancing a mountain on the head of a pin, or a radical rethink. Lisa Randall and Raman Sundrum's breakthrough in the 1990s offered the latter. Their models propose that gravity's strength isn't universal, it's localized. While particles like electrons and quarks are stuck on our brain, gravitons, the hypothetical carriers of gravity, can slip into a warped fifth dimension, their influence dissipating like a voice echoing down a cavernous hallway. This warping isn't uniform. Picture a funnel, narrow at the top where our brain resides, but flaring exponentially into the bulk. Gravity's intensity would follow this curve, appearing weak to us on the shallow end, but potentially explosive near the funnel's base. The implications are staggering. First, it elegantly sidesteps the hierarchy problem. Gravity seems weak because we're far from its source, not because it's fundamentally feeble. Second, it reimagines the cosmos scale. The extra dimension could be microscopic, yet its curvature might hide infinite volumes, like a folded handkerchief concealing vast landscapes in its creases. But how do you test something this abstract? Enter the Large Hadron Collider. If Randall-Sundrum models are correct, smashing protons at near light speeds might briefly punch holes in our brain, creating fleeting gravitational resonances, or even miniature black holes that evaporate instantly into Hawking radiation. So far, no such signatures have appeared, but the search isn't over. Upgraded detectors and higher energies might yet reveal gravity's hidden dimensions, or force us back to the drawing board. Critics argue the theory trades one fine-tuning problem for another. Why is the brain's tension, its inherent energy density, precisely balanced to create the warping we need? Others note that alternative solutions like supersymmetry remain viable, yet Randall-Sundrum's elegance keeps it alive. It doesn't just explain gravity's weakness, it hints at a cosmos far grander and far stranger than we ever imagined. If extra dimensions are real, then black holes might be gateways, not endpoints, and the Big Bang could have been a collision between brains in a higher dimensional arena. The real allure lies in its audacity. Randall-Sundrum doesn't just tweak physics, it rewrites the stage. Gravity isn't a force confined to our world, it's the shadow of something vast and unseen. And that raises a tantalizing thought: if we're just a slice of a higher dimensional reality, what else is lurking beyond the brain, waiting to be discovered? Einstein's general relativity paints gravity as the curvature of spacetime, a smooth, warped fabric where planets and stars roll like marbles on a trampoline. But what if gravity isn't about bending at all? What if it's more like a twisted ladder, its rungs straining under invisible tensions? That's the radical redirection of teleparallel gravity, a century-old idea now staging a dramatic comeback. Here, spacetime isn't curved, it's torqued, with a property mathematicians call torsion taking center stage. Picture a spiral staircase versus a gently sloping hill. Both get you from one floor to another, but one relies on rotation, the other on slope. Teleparallel gravity argues the universe climbs via torsion, not curvature, and this subtle shift could solve some of general relativity's thorniest quantum riddles. The theory's origins trace back to Einstein himself. In the 1920s, while refining general relativity, he toyed with an alternative framework where parallel transport, the idea that vectors should stay parallel when moved along paths, remains intact globally. To achieve this, he swapped spacetime's curvature for torsion, a measure of how much paths twist around one another. Imagine two ants walking straight ahead on a twisted ribbon. They might end up turning relative to each other, not because the ribbon curved, but because it twisted beneath them. Einstein eventually shelved the idea, but recent advances in quantum gravity have breathed new life into it, with physicists asking, what if torsion, not curvature, is the true language of gravity's quantum voice? One of teleparallel gravity's most compelling selling points, it sidesteps the notorious problem of time that plagues other quantum gravity approaches. In general relativity, time is dynamic, it bends and stretches with gravity, but in quantum mechanics, time is a rigid backdrop. Teleparallel gravity offers a third path. By reformulating gravity as torsion, time becomes an emergent property of the twisting geometric structure, not a fundamental ingredient. This could reconcile quantum mechanics and gravity without the philosophical headaches of disappearing time or the mathematical nightmares of singularities. Black holes, for instance, might not be infinitely dense points, but extreme torsional configurations where spacetime's twist becomes so tight it recoils, like an overwound spring. Recent breakthroughs have supercharged the theory's appeal. Modified versions like FT gravity, where T stands for torsion, are now hot candidates to explain dark energy, the mysterious force accelerating the universe's expansion. Unlike general relativity, which needs to patch in dark energy as an ad hoc addition, teleparallel models naturally generate accelerating solutions from the torsion itself. It's as if Einstein's forgotten framework had the answer to modern cosmology's biggest puzzle all along, hidden in its geometric fine print, yet challenges remain. Critics point out that teleparallel gravity struggles to explain certain precision tests, like the perihelion shift of Mercury, as elegantly as general relativity. Others note its quantum extensions, while promising, are still in their infancy compared to string theory or loop quantum gravity, but supporters counter that torsion's mathematical simplicity could be its superpower. Without the need to quantize curvature, a Herculean task, teleparallel gravity might offer a smoother path to a quantum theory. Some models even suggest gravitons could emerge as excitations of torsion fields, like vibrations in a cosmic wire. What makes teleparallel gravity so thrilling isn't just its potential to rewrite textbooks, it's the way it reframes our cosmic metaphors. If general relativity is a symphony of warped space, teleparallel gravity is a jazz improvisation, structured, yet fluid, with torsion as its rhythm section. Whether it's the final answer or just a stepping stone, one thing's certain: Einstein's other gravity reminds us that sometimes the most revolutionary ideas aren't new at all. They're just waiting for the right moment to twist back into view. Spin foam models take the abstract loops of loop quantum gravity and give them a dynamic new life, turning spacetime from a static tapestry into a shimmering quantum dance. Imagine a Feynman diagram, those squiggly lines physicists use to map particle interactions, but instead of electrons and photons, the actors are tiny chunks of spacetime itself. Each diagram becomes a foam of intertwining surfaces, where the edges represent quantum volumes and the faces track how spacetime evolves from one instant to the next. It's as if the universe's history isn't written in ink, but in bubbles, each one a fleeting configuration of geometry, popping and reforming with every quantum fluctuation. This isn't just pretty imagery. Spin foams solve a core challenge in loop quantum gravity: how to describe transitions between quantum states of spacetime. In the classical world, planets orbit smoothly, but at the Planck scale, reality stutters a stop-motion film where each frame is a distinct spin foam bubble. The math behind these models assigns probabilities to every possible transition, like a cosmic game of connect the dots where the dots themselves decide how they'll link up. Some configurations vanish instantly, others stabilize into the spacetime we recognize, like waves calming into glassy water. The connection to Feynman diagrams runs deep. Just as those diagrams sum over all possible particle paths to calculate quantum amplitudes, spin foams sum over all possible spacetime geometries to build a quantum history. But there's a twist: while Feynman diagrams play out on a fixed spacetime stage, spin foams generate the stage itself. This self-referential loop makes them a rare bridge between quantum mechanics and general relativity, a place where gravity doesn't just bend the rules of quantum theory, but emerges from them. Visualizing spin foams requires a mental leap. Picture a hyper-dimensional version of soap suds, where each bubble's surface is etched with quantum numbers representing area and volume. When two bubbles merge, spacetime curves. When they split, it fluctuates. Black holes might form where bubbles cluster into dense knots, their event horizon surfaces where the foam's connections stretch to breaking point. Even the Big Bang could reinterpret as a quantum foam explosion, where a single high-energy bubble fragmented into the froth we now call the cosmos. Yet for all their elegance, spin foams face tough questions. How do trillions of chaotic quantum transitions smooth out into the spacetime continuum we observe? Some answers lie in coarse graining, a statistical trick where microscopic noise averages into macroscopic order, like pixels blending into a clear image. Others suggest spin foams might naturally favor certain configurations, akin to how dice tend to roll 7s more often than 12s. The math hints at a deeper principle: spacetime stability isn't accidental, but a statistical inevitability at large scales. Experimental tests remain distant. Probing Planck scale foam would require particle accelerators the size of solar systems, but indirect signatures might lurk in cosmic phenomena. If spacetime is foamy, high-energy photons traversing billions of light-years could scatter slightly, like light dimpling through frosted glass. Telescopes like the Fermi Gamma Ray Space Telescope hunt for these telltale blurs in distant gamma-ray bursts. Even tabletop experiments with supercooled quantum fluids could simulate foam-like dynamics, offering toy universes where spin foam predictions play out in miniature. What makes spin foam so compelling is their refusal to separate quantum mechanics from gravity's stage. Here, spacetime isn't a backdrop, it's the lead actor, its lines rewritten with every quantum leap. Whether this approach ultimately cracks the quantum gravity code or merely illuminates part of the path, one thing's certain: it's hard to look at the night sky the same way after picturing it as a cosmic foam, bubbling with possibilities. Einstein's universe runs on local rules. Gravity isn't some mystical force reaching across space, but a ripple in spacetime that travels at light speed, touch by touch. But what if that's only half the story? Non-local gravity dares to ask: could gravity's influence leap across the cosmos in a single bound, bypassing the speed limit Einstein set? This isn't magic, it's a radical rethink born from quantum mechanics' messiest corners, where entanglement defies locality and black holes chew up rulebooks. Imagine tossing a pebble into a pond, except the ripples don't spread outward, they appear instantly everywhere, as if the water itself has a hidden hotline connecting every point. The motivation starts with quantum entanglement, that spooky action at a distance where particles mirror each other's states faster than light could carry the signal. If quantum systems can defy locality, why not gravity? Some theorists argue that at microscopic scales, spacetime might be threaded with non-local threads, like a cosmic version of quantum teleportation. These corrections could resolve black hole paradoxes like how information escapes a singularity without violating causality. In non-local models, a black hole's gravity might not vanish at the horizon, but linger as a ghostly imprint, whispering secrets across the universe through hidden quantum channels. But the real kicker comes from cosmology. The universe's large-scale structure, galaxies woven into vast filaments, might not make sense if gravity only acts locally. Dark matter was invented to explain the extra gravitational glue, but non-local gravity offers an alternative. What if galaxies feel each other's tug not just through direct spacetime curvature, but through a web of quantum-corrected, long-range connections? It's like playing telephone with gravity, where the message doesn't hop from one point to the next, it's broadcast to everyone at once. Testing these ideas isn't easy, but neutron stars might hold clues. These ultra-dense corpses of dead stars warp spacetime so severely that tiny non-local effects could pile up over millennia. A pulsar's spin, precise as an atomic clock, could reveal anomalies, like gravity's influence arriving a split second too early, as if it took a quantum shortcut. Others hunt for echoes in gravitational waves, subtle inconsistencies in the signals from colliding black holes that might hint at non-local handshakes beneath the surface. Critics argue that non-local gravity risks reopening Pandora's box of paradoxes, like allowing signals to loop back in time, violating causality, yet supporters counter that quantum mechanics already shattered classical intuitions a century ago. Maybe gravity's next revolution isn't about bending spacetime further, but realizing it was never as local as we thought. After all, if entangled particles can dance in lockstep across light years, why shouldn't the force that shapes the cosmos itself have a few hidden connections up its sleeve? The universe, it seems, still has a flair for the dramatic. What if the universe isn't built on matter or energy, but on information? Not just any information, quantum information, the kind that powers qubits in futuristic computers and binds entangled particles across galaxies. This is the radical shift at the heart of quantum information gravity, a framework where spacetime isn't the foundation of reality, but a side effect of quantum bits interacting in patterns so deep they weave the very fabric of existence. Think of it like a cosmic game of Minecraft. The blocks you see, mountains, rivers, stars, aren't primary. They're just the visible output of invisible code running beneath the surface. The story starts with a profound observation. Black holes obey the laws of thermodynamics. They have temperature, entropy, and crucially, they seem to store information on their event horizons, like cosmic hard drives. But if information is preserved, where does it go when the black hole evaporates? Quantum gravity's answer is startling. The information isn't lost, it's transformed, scrambled into the Hawking radiation itself. This hints at something deeper, that spacetime and gravity might emerge from quantum entanglement, the same spooky linkage that lets particles whisper to each other instantaneously across light years. Enter it from Qubit, a research program that flips physics on its head. Instead of asking how quantum fields live in spacetime, it asks how spacetime emerges from quantum fields. Imagine painting a picture where the canvas itself appears stroke by stroke, emerging from the art being created. In this view, every qubit, every quantum bit of information, is a thread in spacetime's tapestry. Entangle enough qubits and their collective correlations become geometry, curving into what we perceive as gravity. It's as if Einstein's spacetime is the holographic projection of a quantum processor humming in some lower dimensional boundary. The real magic happens with quantum error correction, a concept borrowed from cutting-edge computing. In quantum computers, fragile qubits are protected by encoding information redundantly across many particles, so even if some fail, the data survives. Remarkably, physicists like Leonard Susskind and Juan Maldacena have shown that this same mechanism might explain how spacetime remains stable. Black holes, for instance, could be nature's ultimate error-correcting codes. their interiors shielded by intricate quantum entanglement networks that prevent information from being destroyed. A particle falling in isn't erased, it's encrypted, its data spread across the horizon like a cosmic puzzle waiting to be reassembled. But how do we test such an abstract idea? One clue comes from ADS/CFT duality, the holographic principle's mathematical backbone. In this framework, a black hole in a higher dimensional bulk universe corresponds to a hot, chaotic quantum state on its lower dimensional boundary. Calculations show that disturbing the boundary state, like introducing errors, warps the bulk geometry, as if spacetime itself responds to quantum corrections. It's a hint that gravity might not be a fundamental force, but the thermodynamic cost of manipulating quantum information. The implications are staggering. If spacetime is built from qubits, then black holes aren't cosmic dead ends, they're laboratories for quantum gravity. Wormholes might not be sci-fi fantasies, but entangled quantum channels in disguise. Even the Big Bang could reinterpret as a phase transition, where a soup of disorganized qubits suddenly entangled into the orderly lattice we call the cosmos. Yet skeptics urge caution. For all its elegance, quantum information gravity remains largely theoretical, its equations more at home in supercomputers than particle colliders. But supporters counter that revolution often starts in the abstract. After all, Maxwell's equations were once just scribbles, until they unlocked radio, radar, and the entire electromagnetic age. Whether this framework ultimately unites quantum mechanics and gravity or merely lights the path forward, one thing's certain: it's rewritten the question. We're no longer just asking how the universe works, we're asking how it computes. Einstein's general relativity describes gravity using a single metric, a mathematical ruler that measures the curvature of spacetime at every point. But what if the universe carries two rulers, each ticking to its own rhythm? That's the intriguing premise of bimetric gravity, a theory where spacetime isn't governed by one geometry but by two, intertwined yet distinct. Picture a dancer performing a duet with their own reflection, sometimes moving in perfect sync, sometimes stepping to different beats. In this framework, one metric might describe the gravity we know, shaping planets and stars, while the other lurks in the background, subtly tweaking the rules at cosmic scales where general relativity seems to falter. The origins of this idea trace back to the 1970s, when physicists like Nathan Rosen and later Claudia de Ram, Gregory Gabadadze, and Andrew Tolley explored whether gravity could split into two complementary components. The motivation: dark energy's eerie acceleration of the universe's expansion, a phenomenon that forces general relativity to contort itself with ad hoc fixes, like the cosmological constant. Bimetric gravity offers a sleeker solution. The second metric could act as a cosmic dampener, gently pressing against the first to drive late-time acceleration without mysterious dark energy. It's as if the universe's expansion isn't fueled by some invisible substance, but by the quiet tension between two competing geometries, but the real magic happens in the interplay. These metrics aren't independent, they talk to each other through a mathematical handshake called an interaction term. Think of it like two overlapping grids, one stiff, one flexible, connected by springs that resist stretching. On Earth, where gravity is strong, the stiff metric dominates, ensuring apples fall and planets orbit just as Newton and Einstein predicted. But as you zoom out to galaxy clusters or the universe's vast voids, the flexible metric takes over, softening gravity's grip and mimicking the effects we usually attribute to dark matter. Suddenly, those unexplained galactic rotations and lensing patterns might not need invisible particles, just a second ruler quietly bending the rules. Yet bimetric gravity isn't without its paradoxes. The most glaring is the ghost problem, mathematical artifacts that threaten to destabilize the theory by introducing negative probabilities. Some formulations cleverly sidestep this by carefully tuning the interaction terms, like a chef adjusting ingredients to avoid a spoiled dish. Others argue these ghosts might not be deal breakers, but signatures of deeper physics waiting to be understood. Then there's the challenge of testing. Unlike dark matter models which predict elusive particles, biometric gravity leaves subtler traces, tiny deviations in gravitational waves, or anomalies in the cosmic microwave background. Detecting these requires instruments so precise they'd make a Swiss watch look crude. What makes this theory so compelling isn't just its potential to unseat dark energy and dark matter. It's the philosophical shift it demands, a universe where gravity isn't a monolithic force, but a dialogue between two geometries, each with its own story to tell. Whether those stories ultimately merge into a grander narrative or fade as mathematical mirages, one thing's clear: the cosmos might be holding a second ruler, and we're just learning how to read its markings. Roger Penrose isn't one to shy away from controversy, especially when it comes to rewriting the universe's obituary. His conformal cyclic cosmology doesn't just suggest our cosmos will end, it argues the end is merely a prelude to an infinite symphony of rebirths, where universes rise, expand, and fade in an endless loop. Forget the Big Bang as a singular event in Penrose's vision. It's just the latest encore in a cycle stretching eternally forward and backward. At first glance, the theory sounds like pure poetry. But Penrose backs it with formidable math, hinging on a process called conformal rescaling. Picture this: as our universe expands toward heat death, all matter eventually evaporates into radiation, and distances between particles stretch toward infinity. At this point, something strange happens. The cosmos becomes so vast and cold that the concept of scale loses meaning. A single photon stretched across the void is mathematically indistinguishable from the entire universe squashed to a point. In this state, Penrose argues, the dying universe can seamlessly transform into the next Big Bang without any singularities or paradoxes, just a smooth reset where the infinite becomes the infinitesimal. The real shocker: Penrose claims we might already see echoes of previous universes imprinted on our own. These relics, dubbed Hawking points, are hypothesized to be circular scars in the cosmic microwave background, regions where supermassive black holes from a prior eon evaporated via Hawking radiation, their final bursts of energy leaving faint, concentric ripples in the CMB's afterglow. It's as if the universe has a memory, preserving the death cries of ancient black holes like fossils embedded in spacetime itself. Critics have been ruthless. Mainstream cosmologists point out that the statistical significance of these alleged Hawking points remains hotly debated. Some argue the patterns Penrose identifies could just be random fluctuations in the CMB's noise, a cosmic pareidolia, like seeing faces in clouds. Others note that conformal cyclic cosmology struggles to explain observed features of our universe, like its startlingly low entropy at the Big Bang. If each cycle inherits the previous one's conformally rescaled geometry, why doesn't the entropy pile up, making each new universe messier than the last? Yet Penrose's defiance is part of his charm. He counters that entropy isn't destroyed between cycles, it's erased, reset by the very act of conformal rescaling. Think of it like a chalkboard wiped clean after each lecture. The equations stay the same, but the scribbles vanish. As for the CMB anomalies, he enlists collaborators to sift through ever larger datasets, hunting for more Hawking points with the zeal of archaeologists unearthing a lost civilization. What makes he so captivating isn't just its audacity, it's the way it reframes time itself. In Penrose's universe, there's no true beginning or end, just an infinite succession of cosmic seasons, each with its own black holes, galaxies, and perhaps even life, all dancing to the same conformal tune. Whether the data ultimately vindicates him or not, one thing's certain: in a field often bound by cautious consensus, Penrose reminds us that sometimes the wildest ideas are the ones that stretch our understanding furthest. After all, if the universe can recycle itself, why shouldn't we recycle our boldest dreams? Black holes have long been the universe's ultimate bogeyman, cosmic traps where gravity wins so completely, even light gets dragged into the abyss. But what if these terrifying objects aren't holes at all? Enter gravastars and dark energy stars, exotic alternatives that rewrite the black hole script without the crushing singularities or paradoxes. Imagine a black hole's exterior, the event horizon, the gravitational pull, but peel back the curtain, and instead of an infinite pit, you find something stranger, a bubble of vacuum energy or a seething core of dark energy, pressing outward against collapse like a cosmic tug of war frozen in equilibrium. Gravastars, short for gravitational vacuum stars, were dreamed up by physicists Paul Mazur and Emil Matola as a quantum escape hatch from black hole paradoxes. Their structure is as elegant as it is bizarre. A thin, ultra-dense shell of matter forms the event horizon's stand-in, but inside isn't emptiness or a singularity. Instead, it's a pocket of spacetime filled with negative pressure vacuum energy, a bit like the dark energy accelerating the universe's expansion, but trapped in a stellar-sized prison. This core's outward push perfectly balances the shell's inward crush, creating a stable object that looks like a black hole from afar, but leaves no room for singularities or lost information. It's the universe's ultimate magic trick, a black hole illusion with no black hole at all. Dark energy stars take this idea even further. Proposed by physicist George Chapline, these objects replace the vacuum energy core with something even more exotic, a swirling condensate of dark energy, the same mysterious force ripping the cosmos apart. As matter collapses toward the center, Chapline suggests it undergoes a phase transition, like water freezing into ice, except what emerges is a knot of repulsive gravity. The result, an object that mimics a black hole's exterior but harbors a raging anti-gravity engine inside, potentially explaining bizarre observations like gamma-ray bursts without invoking the headaches of event horizons. The appeal of these models isn't just their cleverness, it's their potential to solve black hole puzzles. Take the information paradox. If black holes swallow information but Hawking radiation leaks it back out as they evaporate, how does the math reconcile? Gravastars sidestep the issue entirely. No singularity means no information loss. Even firewall paradoxes vanish, since there's no true horizon to ignite into a deadly barrier. For dark energy stars, the payoff is cosmic. Their cores could seed bursts of particle production, offering testable links to high-energy astrophysical phenomena that black holes struggle to explain. But could we ever tell these imposters apart from real black holes? The challenge is thornier than it seems. Both gravastars and dark energy stars would bend light and warp orbits almost identically to black holes, nature's ultimate copycats. The devil's in the subtleties. Gravastars might lack the telltale ringing of merging black holes in gravitational waves, since their interiors lack singularities to vibrate. Dark energy stars, meanwhile, could leave fingerprints in the energy spectra of gamma-ray bursts or the behavior of matter at their surfaces. Some theorists even speculate that ultra-precise telescopes might spot light echoes from their cores, faint glimmers betraying the exotic physics within. Yet skepticism runs deep. Critics argue these models require implausibly fine-tuned conditions like vacuum energy densities trillions of times higher than observed in the cosmos to stabilize their structures. Others note that black holes, for all their paradoxes, fit observational data remarkably well without needing exotic alternatives. The LIGO and Virgo gravitational wave detectors have, so far, found no smoking gun deviations from Einstein's predictions that would hint at gravastars or dark energy stars lurking in the cosmic shadows. What keeps these ideas alive is their audacity. They force us to ask, is a black hole's horror show reputation, its infinite density, its inescapable grip, a fundamental truth, or just a failure of imagination? Whether gravastars and dark energy stars are cosmic reality or mathematical phantoms, they remind us that the universe's most terrifying monsters might just be placeholders, waiting for a better story to take their place. And sometimes the boldest theories aren't about proving what's there, but daring to imagine what isn't. Einstein and Rosen never imagined their theoretical bridges through spacetime, those infamous Einstein-Rosen bridges we now call wormholes, would one day shake hands with quantum mechanics' spookiest phenomenon. But here's the twist: what if entanglement, that eerie quantum connection Einstein dismissively called spooky action at a distance, isn't just a feature of particles? What if it's the glue holding the universe's hidden tunnels together? That's the wild promise of ER=EPR, a theory so daring it weaves wormholes and quantum entanglement into a single cosmic tapestry. At its heart, ER=EPR suggests that every pair of entangled particles, those quantum twins that mirror each other's states instantly, no matter how far apart, might be connected by microscopic wormholes. Not the Stargate-style tunnels of sci-fi, but Planck-scale threads of spacetime so tiny they'd make an atom look like a galaxy. This radical idea emerged when physicists Leonard Susskind and Juan Maldacena noticed something uncanny. The math describing entangled particles EPR, named after Einstein, Podolsky, and Rosen's paradox, looked suspiciously similar to the equations for wormholes Einstein-Rosen bridges. It was as if the universe had left a clue, hidden in plain sight for decades. The implications are staggering. Take black holes. If two black holes are entangled, ER=EPR suggests their interiors could be linked by a wormhole, even if their exteriors are light years apart. This wouldn't just solve the black hole information paradox, it would rewrite it. Information swallowed by one black hole wouldn't vanish, it'd surf through the wormhole to its entangled partner, preserved in the quantum fine print. No firewalls, no lost data, just a cosmic game of telephone where gravity and quantum mechanics finally speak the same language, but the real magic happens at the quantum level. Imagine two electrons entangled in a lab. According to ER=EPR, their connection isn't some abstract quantum field, it's a physical bridge, a wormhole so tiny it's practically a mathematical knot. This flips entanglement from a ghostly correlation into something tangible, a spacetime stitch binding the universe's fabric. Suddenly, quantum teleportation, already proven in labs, isn't just particles whispering secrets, it's information threading through spacetime's hidden seams. Critics argue wormholes require exotic matter with negative energy to stay open, and no one's found proof such matter exists, but ER=EPR offers a loophole. Quantum entanglement itself might provide the necessary negative energy, twisting spacetime just enough to keep these microscopic tunnels stable. Others worry the theory blurs causality. If wormholes link entangled particles, could signals hop through, breaking light speed limits? Supporters counter that these wormholes are more like quantum hallways. You can't walk through them, but information can rearrange itself on either end, like a shuffled deck of cards. The boldest claim, ER=EPR, might mean the universe isn't just threaded with wormholes, it's built from them. Every quantum connection, every particle interaction, could be a stitch in spacetime's grand quilt. If true, the cosmos isn't a collection of objects in space, it's a network of relationships where here and there are illusions woven by entanglement's invisible threads. Testing this isn't for the faint-hearted. Some propose tabletop experiments with ultra-cold quantum fluids, where emergent spacetime geometries could mimic wormhole dynamics. Others hunt for anomalies in quantum circuits, where entangled qubits might betray hidden spacetime structures. And then there's the cosmic angle. If wormholes sculpt the quantum vacuum, their imprint might lurk in the universe's earliest light, waiting for telescopes powerful enough to decode it. ER=EPR doesn't just bridge physics' greatest theories, it erases the line between them. Gravity isn't a force bending spacetime, it's entanglement's shadow. The universe isn't a stage, it's a conversation, whispered through wormholes too small to see but too profound to ignore. Whether this vision holds or not, one thing's certain: Einstein's spooky action might be the key to unlocking spacetime's deepest secrets, and we're just beginning to listen. Gravity was supposed to be the universe's great unifier, the force that taught apples to fall and galaxies to dance. Yet here we are, staring at 30 different ways it might break the rules entirely. From loops of spacetime to vibrating strings, from emergent illusions to hidden dimensions, quantum gravity isn't just one puzzle, it's a hall of mirrors, each reflection revealing a stranger cosmos than the last. Take loop quantum gravity's pixelated universe, where space itself is stitched from indivisible threads. Then there's string theory's symphony of hidden dimensions, where particles are notes played on cosmic strings. Or the holographic principle's audacious claim that everything we see might just be a projection from some distant, two-dimensional edge. Even the outliers shock. Entropic gravity suggests gravity isn't a force at all, just thermodynamics in disguise, while E equals BR weaves wormholes into the quantum fabric of entanglement itself. Every theory isn't just a tweak to Einstein's equations, it's a philosophical earthquake, shaking what we thought we knew about reality's bedrock. The beauty isn't in the answers, but in the questions they force us to ask. Can space exist without time? Is gravity just a side effect of chaos? Could the Big Bang have been a bounce from a previous universe? These aren't thought experiments, they're lifelines, pulling us toward deeper truths. And the wildest part, we don't know which, if any, are right. Maybe spacetime really is a quantum foam, or a hologram, or a cosmic Lego set, or maybe the final theory hasn't been dreamed up yet, a revelation waiting in some future lab notebook, scribbled between coffee stains and late-night inspiration. So stay curious, the universe hasn't run out of surprises, and neither should we. Whether the answer lies in twisted geometry, vibrating brains, or something no one's dared to imagine yet, one thing's certain: gravity's final act will rewrite the cosmos. And when it does, we'll be here asking, testing, and wondering what's next.